there are three types of nonlinear functions which can be estimated directly. They do not require linearization. The simplest amongst them is the inverse variation function. The next is the quadratic function, and the third is the cubic function. As you would be aware, the quadratic function has an exponent, has a power 2, and the cubic function has three terms, one linear, the second squared, and the third is a cubic function variable. The nonlinear function has certain characteristics where the variable x invariably has a certain power or exponent, and therefore in general, of course, we would treat this function as y a function of x, but for each of the nonlinear functions we lay out the relationship between y and x. In the case of the inverse variation function, y is equal to f of x to the power of minus 1. In the case of a quadratic function, y is a function of x to the power of 1 and x to the power of 2. A cubic function, y is a function of x to the power of 1, x to the power of 2 and x to the power of 3. After studying this module, you would know about the inverse variation function, about the quadratic function and the cubic function. The inverse variation function is the simplest nonlinear function. Usually it represents physical phenomena. Here we could consider a fixed distance, let us say 1000 kilometers, represented by k. The speed is measured on the y-axis, y, and time taken is measured on the x-axis. Thus, the inverse variation function is measured as y is equal to k upon x, where k is fixed, y and x are variable. We take up an example from the physical world. If a plane travels a distance of 1000 kilometers at different speeds, then we could have a table that charts the relationship between x and y. As we can see here, the time taken in number of hours is given by x, and the speed in kilometers per hour is given by y. So, if the speed is 1000 kilometers per y, that is per hour, that is y is equal to 1000, and therefore the time taken x would be equal to 1 hour, or simply 1. So, when y is equal to 1000, then x is equal to 1. When the distance being the same, if the speed becomes 200, then obviously the time taken would be 5, and so on. When y is equal to 100, the time taken is 10. When y is equal to 66 and 2/3, the time taken is 15 hours. When it is 62 and a half, then it is 16 hours. When it is 50, then it takes 20 hours. When it is 25, then it takes 40 hours. Now, here we are considering the case of a plane traveling at different speeds. Obviously, some of this data is hypothetical because, well, it could be traveling at a speed of 25 kilometers if it is taxiing on the runway within the airport. In this example, however, the speed of the plane is assumed to be exact. This would be true essentially because the plane speed is not affected largely by unknown and uncertain conditions. Therefore, it could actually maintain the speeds which have been written out. Therefore, we have a definite or a deterministic relationship between y and x. In such a case of an deterministic relationship, the relationship between x and y is exact, and there is little point in trying to measure it empirically. Similarly, there could be more such physical phenomena that could be plotted and could have a definite or deterministic relationship. For example, we know that if pressure increases, suppose x is pressure, x variable is pressure, and pressure increases, then volume decreases, therefore y decreases exactly, and there is a definite relationship or ratio or proportion between the two. This physical phenomena could just be plotted and the figure would show an exact relationship. Now, we could look at where there is a smooth relationship between speed and time of travel taken by a plane. However, if we take a similar example of a car, when it actually travels on the road, there would be some frictions and obstacles. When we measure and plot such a curve, it would not show an elegant or smooth pattern. On the y-axis, we have measured kilometers per hour, and on the x-axis, we have taken time. To begin with, for a distance of 1000 kilometers, obviously the time taken would be 1 hour. However, initially, as the speed falls to 200 kilometers, the time taken rises sharply, hence the curve falls suddenly. Thereafter, the speed falls, but it falls gradually. Therefore, time taken rises, but rises slowly. As speed falls, the curve becomes more and more flat as it approaches the x-axis. This technically continues up to infinity. This is an asymptotic property of the inverse variation function. You could view this property in figure where the inverse variation function shows how constantly the speed is declining, and as the speed declines, the time taken to cover the same distance goes on increasing, and this curve becomes asymptotically parallel to the x-axis. Now, let us just consider how this would pan out. If the speed in kilometers per hour is 100, then in this case the time taken would be 4.76. When the speed goes down to 70, then it is 5.12. When it goes down to 50, it is 9.29, and so on down to 40, 35, 25 and 20, and respectively the time taken is increasing from 9 to approximately 10, 13, 16 and 21. Now, in this table, we therefore are looking at the relationship between the travel time of a car and the speed of the car. As I said earlier, in the case of a plane, there are no frictions, there are no obstacles and no restrictions. Therefore, the relationship is exact and smooth. But in the case of a car, if we are traveling a distance of 400 kilometers, then you would notice that the time taken is not exactly 4 hours, but it is 4.76 hours. Similarly, if the speed is 50, the time taken should be 8 hours, but it is actually 9.29 hours. For 40, it is 10.69 and not exactly 10 hours. So, in the following figure, you would notice that the relationship between speed and time in the case of a car which is traveling on the road is not exact. It is not a smoothly following path as we have seen in the case of a plane. Therefore, figure shows the relationship between the car traveling at a speed of y and the time taken being x does not exactly look like the same curve which we have encountered earlier. The real world frictions cause minor variations in the relationship in the case of a car travel, and hence the equation needs to be redefined in stochastic terms. So, we would say that y is equal to k by x plus ut, ut being the error term which is the stochastic error term. When ut is an error term, it gives a difference between the exact measure and the actual measure of time taken to travel 400 kilometers. This happens because of frictions and obstacles on the road, unlike air travel. Now, let us take another example from economics, that is from the case of the cost curves. The average fixed cost is a prominent example which is based on the inverse variation function. There is a very similar exact relationship in respect of the average fixed cost and quantity of output. AFC is measured on the y-axis and quantity of output is measured on the x-axis. We know that the total fixed cost is given. Let us say that the total fixed cost is 40,000 rupees. Now, if we plot the average fixed cost against the quantity of output, then we get a smooth relationship. In this case, the total cost, which is 40,000 rupees, has to be simply divided by the quantity of output x. The obvious conclusion, as the output increases, AFC will fall proportionately and, mind you, exactly. The mathematical inverse function is an exact hyperbola. If we apply this concept to production theory, then we have a rectangular hyperbola. Here, average fixed cost into quantity will always be equal to k, which is a fixed number, which is nothing but the total fixed cost. The area under the curve will always be equal to k, which is the total fixed cost or a constant. So, average fixed cost, which is measured on the y-axis, would actually be 40,000, which is k, divided by quantity, which is the x variable. The relationship between the average fixed cost which is measured in height and the quantity of output which is measured on the x-axis. So, you would notice that when the quantity is 100, the average fixed cost is 400, 120, so the average fixed cost is 33, and so on goes as the output goes on increasing, the average fixed cost goes on declining, but it declines in a very elegant, smooth manner without any bumps, without any restrictions, without any obstacles. The average fixed cost is an asymptotically parallel to both the axes. As we move up, it becomes parallel to the y-axis, and as we move down towards the x-axis, it becomes parallel to the x-axis. As the output increases, the average fixed cost reduces and it actually never touches the x-axis. Another feature of this function is that as the AFC is falling, in successive units of output, the change or the fall or the decline in the average fixed cost goes on declining. In the first instance, if we look at the change in the average fixed cost, it is 67. It goes down to 48, to 36, to 28, 22, 18, 15, 13, 11, 10, 8, 7, 7, 6 and 5. We notice two things over here, that the fall in average fixed cost is going down, and at one point there is a number which is being repeated, 7, 7. Now this is known as the point of inflection. The fall in the average fixed cost shows that a rectangular hyperbola has got a certain property. One feature of an inverse function is that the second derivative is negative, that is, the second derivative would keep falling. In other words, the rate at which AFC falls in relation to output is falling. For each successive unit, the increase in the output of AFC falls slower and slower. The average fixed cost will have a slope which slopes downwards continuously and approaches the x-axis but never actually touches the x-axis. It is smoothly going down. It comes down to a point of inflection where it becomes flat almost, and it becomes flatter and goes parallel to the x-axis. Now let us consider in figure the relationship between total fixed cost and average fixed cost. We have 2 points to consider over here. When the average fixed cost is 400, then we have 100 units are being produced. So TFC1 is equal to 400 into 100, which is again 40,000. On the other hand, when the average fixed cost is 200, then the production would be 200. 200 into 200 would again be 40,000 rupees. This way, in general, we can say that AFC into Q is equal to TFC. Therefore, the area under the curve will always be constant, which means that in figure we can see that TFC1 is equal to TFC2. Now, let us consider the quadratic function. Another nonlinear function is a quadratic function. In a quadratic function, the independent variable x is raised to the power 2. Let us look at a simplest quadratic function which has got the equation y is equal to x squared. The table of x and y values of this function might look like this, that is, x is one column and y or x squared is the other column. So suppose we start with minus 3, minus 2, minus 1, 0, 1, 2, 3. Then the square would be 9, 4, 1, 0, 1, 4, 9. So this is how a quadratic equation looks. If we transform this into the form of a diagram, into the form of a curve, and we plot it, it looks like a parabola whose center is at the origin. On the left hand side, in the negative quadrant, the second quadrant, we find that as the value of x goes down towards, it increases from minus 6 to minus 4 to minus 2 and so on up to 4, then the quadratic equation, the quadratic form is the equation, the curve is going down. When we take up another dimension, we would be looking at cost theory. We know that the average variable cost is a U-shaped curve. For capturing this, we need to consider not only output but the square of output. Is the relationship between output and the square of output. Suppose the output is 100, then the square of output will be 10,000 and so on, 100, 120, 140, 160 and so on. So although the output is increasing by constant amounts of 20, you would notice that the square of the output is increasing, as we call it, geometrically. The quadratic output, this is what we would call the quadratic output. The quadratic equation for the average variable cost is given as ABC is equal to A minus B1 into Q plus B2 into Q squared plus UT. The alternation of signs is something that we can note. If B1 is negative and the average variable cost, since the average variable cost first falls and then rises, then we have the next term which is B2, which would be positive. And similarly, if we have a curve which is not a U-shaped curve but an inverse U-shaped curve and like a bell curve, then what would happen is that B1 would be positive and B2 would be negative. That means the linear term would be positive and the square term would be negative. Now it all depends upon what kind of a equation it is. Is it a U-shaped curve or is it a bell-shaped curve? Now let us fit a quadratic function. The average variable cost is measured, and in tables we have the quadratic curve. This is the actual average variable cost. And how do we actually derive the property of a quadratic equation? Let us observe the average variable cost curve. In figure we see that as x is increasing from 1, 2, 3, 4 up to 10, 11 and so on, the average variable cost is declining from around 450 gradually to 400, 350, 250 and so on. At some point round about 267 we notice that or 265 we notice that the slope is given by the tangent at C. Before this, the tangent at A and B have got a higher slope. At C, the slope is 0. Now, this is again a point of inflection. After this, when we look at the slope at D, it increases. At E, it goes even further. So, we have a definite pattern. At A, it starts to decline, at B, it declines further, at C, it is 0, at D, it starts to rise, and at E, it goes even further. So, this is the typical pattern of a quadratic equation. The average variable cost at a particular point of time we know is given by the slope of the average variable cost, or it is measured also from the slope of a ray from the origin on a point on the total variable cost curve. At point A and B, the value of the slope of the average variable cost is falling and declining continuously. At point C, it is the minimum point, and thereafter it rises. This is the property of a U-shaped cost curve. Here we have got the cost estimates and the output, the total fixed cost, the quantity, the average fixed cost, average variable cost, total variable cost, and then we have the total cost. You would be noticing that most of these functions are, all of these functions in fact are non-linear. Of course, quantity is a linear variable which is just being measured on the x-axis. Now let us try to estimate a quadratic equation with the help of regression analysis. Here you would notice that the coefficient, there are 4 coefficients. The first is the intercept, the second is the slope, the third is again the coefficient or slope of the square term, and the fourth again is the slope of the cubic term. So, what are we now looking at? We are looking at a cubic term which is a total variable cost, and total variable cost has got 4 coefficients. So, as we have said earlier, there is an alternation of signs. First, the coefficient of the linear term is positive, that means the total variable cost rises. Then after a point, the coefficient of the quadratic term is negative, which means the total variable cost starts to rise. It is rising, but it rises at a declining rate. And after a point, again there is a point of inflection and it starts to rise at a rising rate. So this is how a cubic function behaves. TVC is equal to A plus B1Q plus minus B2 Q squared plus B3 Q cubed. We have fitted a total variable cost curve, measured a total variable cost curve, and the equation reads as TVC is equal to A, which is the intercept, which is 29709.81, and then we have the first coefficient, the linear coefficient, which is 668.43, it is positive. The next coefficient is minus 3.07, which goes along with the square term. Then again we have an alternation of signs, it is positive 0.007, which goes along with q cubed, and the error term ut. Here from the equation it is evident that the coefficient of the linear variable is the highest, it is largest in magnitude. The quadratic variable has got a relatively smaller coefficient, and the cubic variable has got the smallest coefficient, it is merely 0.007 in comparison to the linear terms coefficient, which is 668. So this is because when q rises, the linear coefficient is very large, but q itself is very small. As q increases slightly, the square of q becomes very large, and then to balance it out, the coefficient becomes small. As q rises further, the cube term, cube of q quantity, becomes extremely large, and therefore to balance it out, you have a very small coefficient of the cubic term. So this is how it operates, and we can see that if we look at the slope of the total variable cost in figures, then at various levels q1, q2, q3, q4 and q5, you could easily see that A, B, C, D and E are points at which initially the slope is high at A and of the ray from the origin, which is again the average variable cost, and then at B it declines, the slope declines. At C it goes down further, but after C there is a point of inflection where at D and E the average variable cost increases because the ray from the origin, the slope of the ray from the origin increases further. So this actually traces the shape of the average variable cost from the total variable cost. So this is what we can see, how we have a relationship between a cubic function and a quadratic function. So a cubic function is S-shaped, whereas a quadratic function is U-shaped, but there is a definite relationship between them, one of a fall and an increase, which is depicting a very specific relationship between the two. Now let us summarize. There are three types of nonlinear functions which are directly estimated. One is the inverse variation function, the quadratic function and the cubic function. The inverse variation function is the simplest nonlinear function which represents physical phenomena. In the quadratic function, the independent variable has a term which is raised to the power of 2, and in a cubic function we have three terms: the linear component, the linear part of the cubic function, the quadratic part which has the power 2, and the cubic part, and it has a peculiar pattern, a rise fall and again it rises. And then we have seen that there is a relationship between a cubic function, which is total variable cost, and average variable cost, which is a quadratic function.